Welcome back, everybody. Yep. Yep, Cody, they are. That's a lot of carbs. Yep. I'm about to go work out for 3 hours after this. I'm not even kidding. Why 3? Well, I have workouts where I do an extended workout like that because it allows you to hit more volume because you can rest for longer. But not all my workouts are like that. Sometimes I'll work out for 45 minutes where I'll just be a lot more intense. I go for an hour. There's nothing wrong with that. Yeah, there's nothing wrong with just doing it for an hour, and I do that sometimes. But sometimes it's good to sack the muscle and do it for 3 hours. What's really good is to throw your body, like make it confused. Like work out for an hour regularly, and then out of nowhere work out for 3. And out of nowhere just work out for 45. All the while changing the intensity appropriately. Where your shorter workouts are higher intensity and your longer workouts are lower intensity, but higher volume. That's a very good routine, Cody. That's a good routine. Okay. Where were we? Okay, all right, over here. So once we got to this point right here, we aspired to solve for x. So what we want to do is we want to take the square root of both sides here. So that means I get x minus 1 is equal to plus or minus the square root of 20 over 3. And I can distribute that square root to both 20 and to 3. Why would I do that? Well, because 20 is really 2 times 10, which is 2 times 2 times 5. Okay. 2 times 2 is really 2 squared. And I can distribute that radical. So I get the square root of 2 squared, which is 2, and then root 5 stays there and root 3 stays there. So then I get x minus 1 is equal to plus or minus 2 root 5 all over root 3. And if we really wanted to, we can rationalize the denominator, multiply top and bottom by root 3. So I get 2 root 5 times root 3 all over 3 over here. Then I can add a 1, and I get what x is. I get x is equal to 1 plus or minus 2 root 5 root 3 all over 3. Okay. And so establishing a common denominator, I get x is equal to 1. Multiply top and bottom here by fancy number 1. Multiply top and bottom by 3. So I get 3 plus or minus 2 root 5 root 3, everything all over 3. Then one of the roots is when we elect to add our x plus 3 plus 2 root 5 root 3 all over 3. Then the other root is 3 minus 2 root 5 root 3 all over 3. Albert is locked out. Can you invite him? I invited everybody. I see Albert in here. I'm here. Okay. I don't know what Jay was talking about. For the math, where did you get that x minus 1? Over here, we got that x minus 1 from way back here. We started out with 3x squared minus 6x minus 17, and we aspired to solve this quadratic equation using completion of the square. So we added the constant term and to both sides, and then completed the square, which meant we add a 1 to both sides. Afterwards, what was on the left-hand side, this thing right here, factors to an x minus 1 quantity squared, okay? And then we took the square root of both sides here to get just that x minus 1, because the square root of anything squared is just itself. So the square root of the quantity x minus 1 squared is just the quantity x minus 1. Does that make sense, Kiana? Was it Kiana or Kiona? Number 1 for Kiana, number 2 for Kiona. Kiana or Kiona? Oh, so it's 2, Kiona. All right. So that's another technique. Completing the square allows you to factor. Let's use another technique that you guys are familiar with. Let's say I have a 3x squared minus 2x plus 10 is equal to 0. Okay. This is very hard to factor. And of course, we could use completion of the square. Completion of the square always works. Factoring doesn't always work. It's very difficult to factor all the time. But we have another tool in our arsenal, another weapon in our arsenal, and that's the quadratic formula. Okay? The quadratic formula states that x is equal to negative b plus or minus the square root of b squared minus 4ac all over 2a. And this is derived from ax squared plus bx plus c is equal to 0. And I'm going to assign a bonus problem. I would be very impressed if you guys solve this, and I'll give you some extra credit on your first exam. Bonus. Derive the quadratic formula. So derive this formula. So I'll give you a hint. Complete the square for ax squared plus bx plus c equals 0. Once you do that, you will be able to derive this equation, x equals negative b plus or minus the square root of b squared minus 4ac all over 2a. I had some teacher in high school sing some song like x equals negative b. I was like, with all due respect, ma'am, why are you singing out here? Why can't you just justify it? I was not that professional and cordial with her back when I was a student. I think I said something like, do you even know where that comes from? Why are we doing this? I hate math. I hate school. I hate life. Something like that. I didn't really hate life. I hated the life that I was forced to live. And I'm sure everybody here who was forced to do math without having the math explained to them well was a nightmare, wasn't it? Okay? But we can solve this right here using the quadratic formula. And for bonus, if you derive the quadratic formula by completing the square of this, I'll give you maybe 4 or 5 extra bonus points on your first test. How about that? So let's apply the quadratic formula here. That means x is equal to negative 2. So it's going to be positive 2. Plus or minus the square root of b squared, which is my negative 2 squared, minus 4 times A, which is 3, times C, which is 10. Everything divided by 2 times A, which is a 3. Okay, so then this is equivalent to positive 2 plus or minus the square root of 4 minus 120. Because 4 times 3, oh my goodness. 4 times 3 is 12, times 10 is 120, all over 6. I said, oh my goodness, because again, we're going to be taking the square root of a negative number. Okay? But that's fine, you know, it doesn't matter. The book, your homework problems won't put you in this position, and your test problems won't put you in this position. But really, it's no different when you're not in this position. All you got to do is know what the square root of a negative number ends up being. So what's the square root of 4? It's plus or minus 2. What's the square root of negative 4? It's just plus or minus 2. But all you got to do is now just put an I there. It's not that hard. It's not a big deal. I hated doing this. Yes. Yes. Okay, so even though we get a negative number, it's not that big of a deal. Okay, so bringing the calculation over here, I get x is equal to 2 plus or minus the square root of 1/16 with a negative on it, everything divided by 6. Okay, so let's see, so okay, so then this is 1/16. Let's see. So 1/16 is really 58 times 2. All over 6. And 58 is really 2 times, well, I know 2 times 25 gives me 50. And 2 times 26 would give me 52. And 2 times 27 would give me 54. 2 times 28 would give me 56. So 2 times 29 should give me 58. Right? And there's a negative here. Don't forget our negative. And let's not forget we're dividing everything by 6. And let's not forget that this is equal to our x. Okay? So then x is equal to 2 plus, notice that these 2's can combine to give me 2 squared. Square root of 2 squared is just 2. And then when there's a negative, there's an I there. So this becomes plus or minus 2I root 29. Everything divided by 6. Okay? And we can technically write this as x is equal to 1 plus or minus I square root of 29, everything divided by 3. Because 6 is really 2 times 3, and I can factor out a 2 and cancel. So this is what I mean by that. Okay, so that means, you know, we're done. One of our x's, x plus, is when we elect to add. So it's just 1 plus this I square root of 29 all over 3. And we have an x minus is when we elect to subtract. That's equal to 1 minus this I square root of 29 all over 3. So guess what, guys? I'm making you do stuff that's more advanced, more advanced than what's required for this class. So that means if you get this stuff, you'll easily get what is going on in the actual lecture and the material. Let's do another quadratic formula application. Let's do, and I hopefully this time I won't get a complex number here. So how about I pick a negative c? So how about I get 7x squared plus 3x minus 7 is equal to 0. Let's solve this using the quadratic formula. So x is equal to our negative b plus or minus the square root of b squared minus 4ac all over 2a. And for those of you who will go do the bonus, you will see why this is true as a consequence of completing a square for the arbitrary ax squared plus bx plus c is equal to 0 quadratic equation. But then just putting in numbers here, I get our negative b is just negative 3 plus or minus the square root of b squared, which is 3 squared, which is 9, minus 4 times my 7 times my negative 7, all over 2 times my a, which is 7. So I get x is equal to negative 3 plus or minus the square root of 9 plus 7 times 7 is 49. 49 times 4 is 196. So I get negative 3 plus or minus square root of 9 plus 196 all over 14. So I get this is equal to negative 3 plus or minus the square roots of, what's 9 plus 196? Well, when I add 4 to that, it becomes 200. Then what's remaining is 5, so it's 205. Okay. 205 seems like it's divisible by 5. Yeah, 41 times. 5 can go into 205 41 times. So I can break up 205 to 41 times 5. Okay, 41 seems like a prime number, and 5 is a prime number, so it doesn't break down any further than that. I was just checking to see if it would break down anymore, but it doesn't. So that's our answer, and no complex numbers this time. X plus will be negative 3 plus my square root of 205 divided by 14, and x minus is when we elect to subtract. That's negative 3 minus the square root of 205 all over 14. There's our two answers. So we've solved quadratic equations using factoring. We solved quadratic equations using completion of the square, and we've solved quadratic equations using the quadratic formula. Okay. And recall you had that other way of solving quadratic equations, and that is by grouping, factoring by grouping. So let's say you have some 4x squared plus 15x plus 9 is equal to 0. All right. I'll review factoring by grouping one more time. So what you want is to find see this problem here. Okay. Factoring by grouping. The way you do this process is you get your A times your C which is 4 times 9, which is 36, right? And you find all the factors of 36 such that a pair of factors adds up to 15. So 36 has factors 1 times 36, but that's equal to 6 times 6. But, 6 plus 6 is 12, and that doesn't equal 15. So we'll keep searching. But that's the same thing as 2 times, no, that's the same thing as 3 times 12, right? That's also 15, right? So 3 times 12 is also 15. Oh, wait. 3 plus 12 is also, it adds up to give me 15. And 3 times 12 equals 36. So factoring by grouping says that this is what you want to do, is you get your AC, you multiply your A number times your C number, which is 4 times 9, and you get 36. Then you break down it to different factors and see which pair of factors adds up to be equal to your B term, your 15. Once you found that pair of factors, you'll split up your B term with the values of those pairs of factors. So by that, I mean, I want my 15x to now be re-represented as a 3x plus a 12x. So I'll rewrite this equation. That's 4x squared plus 3x plus 12x plus 9. That's equal to 0. This allows us to now do the factoring by grouping, because we'll get a group here and factor something, and we'll get a group here and factor something. And then once we do that, we'll factor again, as you'll see. Notice that these two first terms have the value x in common, so we can factor that out. So then I get 4x plus 3 over here. And notice that these two terms here, so these guys had an x in common. Notice these guys over here, they have a factor of 3 in common. So I can pull out a 3. And so I get 4x plus 3 over here. And that's equal to R0. Any questions so far? This is what we did last class. I'm just reviewing it. We're doing one more example. Okay? So then notice that this term and that term also now have something in common. This quantity 4x minus 3. So moving the calculation up here, I can pull out that quantity 4x. Did I say minus 3? I meant plus 3. We can factor that piece out, and that what remains is this x plus 3 equaling 0. So we've done it. We've represented this quadratic equation as the product of two values. So that allows us to use the zero product rule, which means I get 4x plus 3 is equal to 0. That's a possibility. And also my x plus 3 is equal to 0. That's another possibility. This one gives us that x is equal to negative 3 when we solve for x. This one gives us x is equal to negative 3 over 4 when we solve for x. And that's because whenever you subtract the 3, you get 4x is equal to a negative 3. Then you divide both sides by 4. And so you get x is equal to our negative 3 over 4. No QS. Oh, does that mean questions? Okay, good. Any questions now? Okay. So we'll be moving on to section 2.6. So let me find that here in our textbook. Okay, now we're going to be solving equations with rational exponents. Rational stems from the word ratio. So rational stems from the word ratio, and a ratio is a comparison between two quantities. So really, it is some x over y, where x and y are real numbers. So a rational number is a fraction, if you will, a division of two numbers. So we want to know, for instance, what is 8 raised to the 3/2 power equal to? What does this even mean? Can we evaluate what 8 to the 3/2 power equals? And the answer is yes, because recall some quantity x raised to the m over n power. This is by definition the nth root of x raised to the m power. So applying that to my 8 raised to the 3/2 power, that means I'm taking the square root of 8 cubed. Okay. But what is that? Well, I'm not going to cube 8. That's too hard. It's going to make my brain hurt. Okay. But what I can do is I can say, okay, this is the square root. 8 is really 2 cubed, isn't it? Yeah, it is, because 2 times 2 is 4 times 2 is 8. That means 8 is 2 cubed. So I can replace 8 with the 2 cubed. So I get 2 raised to the 3rd power raised to the 3rd power. Recall, x raised to some m re-raised to the power p. In general, the powers are multiplicative. You get x to the mp. This is opposed to when I say x to the m times some x to the n, where the exponents add. Here we're taking two common bases with two different powers and the exponents add. So for instance, 2 cubed times 2 to the 7th would be 2 to the 10th. All right, that's an example there. Over here, you're saying something already had a power, and now I'm raising that thing to a new power. So it's got a power and it has a higher power. And so what happens to the powers is the powers multiply. So applying that here, this is 2 raised to the power 3, raised to the higher power 3. So the powers multiply. And so I get, this is 2 raised to the power 9. So it's 2 raised to the 9th power. 8 to the 3/2 is really the square root of 2 raised to the 9th power. Okay. But really, 2 raised to the 9th power, let me take the square root of that. That's really 2 squared times 2 squared times 2 squared times 2 squared times 2. Why am I saying that? Because apply this concept here to this. All of these have the same base here, 2, 2, 2, 2, 2. And so whenever I multiply two mathematical objects that have the same base raised to a power, the powers add. So I'm going to get this 2 plus 2 plus 2 plus 2. These add up to 8. So how does that 9 come about? Well, it's because this is also a 1. So 2 plus 2 plus 2 plus 2 is 8, plus the 1 is 9. That's why I can say that these are equivalent. But then the square root can distribute to each of these guys. So this is equal to the square root of 2 squared times 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 the square root of 2. That doesn't even look like a 2 anymore. Right? So each time I distribute a square root to a 2 squared, it becomes just a 2. And I got 1, 2, 3, 4 of them. So I got 2 times itself 4 times, right? So that's 2 raised to the 4th power root 2. But what's 2 raised to the 4th power? Well, I know 2 cubed is 8. So it's really 8 times 2, which is 16. So this becomes 16 square root of 2. And that is what 8 raised to the 3/2 power is. It's 16 root 2. Again, it's saying that Any questions so far? We have like 9 minutes again until it kicks us out. No, good. If anyone has any questions, let me know. No questions. So what about 64 raised to the negative 1/3 power? What does that mean? Well, recall, again, x to the m over n power is the nth root of x to the m. But x to the negative m over n power is the same thing as 1 over x to the positive m over n power. Which then that means this disappears in the denominator here. Keep that in mind when we compute this guy, 64 raised to the negative 1/3 power. This is the same thing as 1 over 64 raised to the positive 1/3 power. Okay? And so this is the same thing as 1 over 64 cube root of 64, and then 64 is raised to the first power. Anything raised to the power of 1 is itself. So I can just forget about this right here. So what is the cube root of 64? I really don't know. I know, let's think about what 64 equals using the fundamental theorem of arithmetic. That's really 32 doubled, right? Doubling 32. So then that's really 2 times, what's 32? 32, we can get that if we double 16, right? Because if I double 15, I just get 30. If I double 16, I would get 32. And so what is 16? That's, if I double 8, right? 2 8s give me a 16. But what is 8? That's just me doubling a 4. Well, what is 4? Oh, that's just me doubling a 2. Hey, that kind of rhymed. 1 2 3 4 5 6. 1 2 3 4 5 6. Okay. So these are all multiplied into the same base, and they all have powers of 1. So when you multiply, so this is the same thing as 2 to the 6th power, right? So 64 is the same thing as 2 to the 6th power. That's going to help us take this cube root here, right? That's going to allow us to help us to take this cube root here. I'm so glad that we reviewed the fundamental theorem of arithmetic, because I get to show it to you again and again and again. 64, which is a composite number, it's not prime, means that you can break it down to a product of just prime numbers. 2 is prime, so boom, boom, boom. And so notice that this right here, 2 to the 6th power is the same thing as 2 cubed times 2 cubed. Because whenever I have the same base and I multiply them, their exponents add, so 3 plus 3 is 6. That's why I can write this. And just like the square root, the cube root also does this distribution process across multiplication and across division. So what's the cube root of 2 cubed? It's just 2. The cube root of 2 cubed is just 2. So then I just get, this is a pair of 2's multiplied times each other. Means I get 1/4 as my final answer. So 64 raised to the negative 1/3 power is 1/4. Isn't that crazy? That's really cool. Because we're able to define negative powers. And not only that, we have the audacity to define rational powers. That's amazing. Oh, what was that? Are you guys wondering if we are able to define complex powers? Meaning numbers raised to I? How do you get the 22? How do you get the 22? Joseph, we don't have a 22. It's a 2 times 2. And that's a consequence of the fact that the cube root of 2 cubed is 2. And it's being multiplied times another cube root of 2 cubed, which is also 2. So then we say 2 times 2 in the denominator. Does that make sense, Joseph? Oh, okay. Oh, good. When you have a number raised to a fraction, how come the denominator goes on the outside of the root? Oh, you're talking about this right here. Good question. That's just how mathematicians have defined it. And it's a reasonable definition. It's a reasonable definition because it adheres to the way numbers add power-wise normally. Because, you know, if you had remember x squared times x cubed, really the way we figured out, we know by that rule that this is x to the 5th because we add the exponents. But really we could have done it the hard way, like this, and counted how many x's we have. So mathematicians historically found trends, and they realized that, hey, this works for integers, but what if I wanted to add x to the 1/2, or what if I multiply x to the 1/2 times x to the 1/2? Surely by this rule that works for integers, this should uphold to be x to the 1, right? So they thought to themselves, surely that means we should be able to construct mathematical notions that allow us to adhere to this. And that's when the idea of a square root got invented, because the square root is precisely that mathematical object that when you multiply the square root of x times the square root of x, you get x. Why? Because that's just the square root of x, all of it squared. And to square a square root, by definition, undoes the root. It undoes the radical. Does that answer your question, Jay? This is how mathematicians originally thought of the idea of taking a square root or even a cube root, because this argument could have translated to, and I love that you asked these questions. This argument could have translated to x to the 1/3 times x to the 1/3 times x to the 1/3, because that's the same thing as x to the 1/3 plus a third plus a third plus a third plus a third, I'm a nerd, equals x to the 3/3, which is x to the 1, which is x. So then mathematicians ponder